Hello everyone. Today we'll be discussing about the importance of stress tensor and equilibrium equations and the relevance of the equilibrium equations inside the deformable body. So let's start. So first we would like to give you a brief review of what we have done earlier, because we've already talked about what exactly stress tensor is, and it has been represented by a stress vector. So we will going to see our familiar example of a bending of a beam. If you have a body like this, and it is being loaded by some load P, then we know that at every cross section of this body there will be some particular kind of normal. We will represent this cut face by a normal, and at each point is represented by a stress vector which is equal to a stress tensor times the normal face Nj. This we have earlier already seen. Now it's important to review that these are the vectors and these are the second order tensor. So I would like to convince you on this point that the importance of second order tensor is what is required on this plane rather than the vector as a whole. So we know that the stress tensor sigma ij is equal to our normal stresses and some shear stresses. xy, xz, xy, xz, and this will be tau, yx, yx, yz, and this will be tau, yz. Both are same, so we can write like this. So this was our stress tensor, and we know that it has 9 components, and because of the symmetry of the stress tensor, it has been reduced to 6 components. Now I would like to convince you why the stress tensor is important rather than the stress vector. The stress vector as a whole is not important for us. The importance is what the stress tensor sigma ij is, because stress tensor consists of several important 6 components, like 3 normal stresses and 3 shear stresses. Because practically what kind of loading we have been directly exposed to these components only, not the stress vector like this. Like for example, if we have some kind of a tensile loading and a load is applied like this, P, I can also write this like this, P by A, so this becomes stress. So if such kind of loading is applied, and I know that if this is, for example, a material called as aluminium, and the failure stress for the aluminium I know is 460 MPa, then, and I used to represent the axial loading as X and the non-axial as Y. So this will be an axial loading X. So I know that the failure stress is 460 MPa. So the effective stress component is only sigma xx. So for me, for component, for not to fail, the sigma xx should be smaller than sigma fail, which is 460. So what comes in here? Sigma xx. So this becomes my important component. In a similar way, if I have a loading in this direction, let's say I fix this body and I'm loading this, then my sigma yy component will be effective. In the same goes to the other third normal component, sigma zz. So as a component wise, they are important in the practical applications. For the case of shear also, you can take, let's take this example for shear. Let's say you have been given two types of butt joint like this. Load is P by A, and this is, let's say this is fixed. So when load is applied on this, then there will be a shearing effect occurring here. This plane would like to shear together. So if this is my x and this is my y, then the component here is tau xy. So if my failure load here for failing is 100 MPa, that means this bond here composed of, the strength of the bond is 100 MPa, then my shear stress should be smaller than this bond failure strength. If it becomes greater than, then this bond will fail. So what comes here again? A stress tensor component. So I would like you to convince on this that these stress tensor components are important. That means the stress tensor is important on a plane rather than a stress vector. So from now onwards, we'll talking only about the stress component, because they are important, not about the stress vector. So let's move on to the second topic, which is equilibrium equations. Now we have seen that when we were earlier in the first year engine mechanics course, you have seen a rigid body dynamics. You have studied rigid body dynamics. So in the rigid body dynamics, you have seen that you have a rigid body and different forces has been applied on this rigid body. Some moments has been applied on this rigid body. And for static equilibrium, the summation of all the forces must be equal to 0. Similarly, for static equilibrium, summation of all the moments must also be equal to 0 for this body, for the body to remain in equilibrium. And this summation of all the forces equal to 0 was called as principle of linear momentum, and this was called as principle of angular momentum. So if the principle of linear and angular momentum is satisfied on the body, then my body is said to be in equilibrium. Something very similar will be happening in the case of deformable body also that we have taken. So the deformable body that we have taken, I am taking the same example again and again. It is being loaded now. I want to ensure that at each and every point my body is in equilibrium. It is in stationary position, it's in equilibrium position. So what I need to do? I need to correlate this. I need to verify the principle of linear momentum and principle of angular momentum. These two I need to do. Now, as you have seen earlier, I hope you have done a small hands-on that I have shown earlier, I have given earlier. I asked you to prove that the stress tensor is symmetric. To show that the stress tensor is symmetric, what we need to do? We need to take the moments of the components of the shear about the fixed coordinate system. So what we used to do, summation of all the moments equal to 0. When we used to do this, then the stress tensor becomes symmetric. So now our stress tensor is symmetric. That means the principle of angular momentum is already satisfied. So what I need to do more? I need to satisfy the principle of linear momentum. Once this whole principle of angular and linear momentum becomes satisfied, then my stress tensor at each and every point will become equilibrium. So to do that, I need to obtain some equilibrium equations, and I'll be obtaining these equilibrium equations using the principle of linear momentum. Okay, so let's do this. Now before we go on to do this, let's talk about two kinds of forces. In general, there are two kinds of forces. Two kinds of forces that are applied on a body. So one is a surface force and the other one is the body force. Now I would not like to go in the semantics of this. I would directly tell you what these forces are. Surface force is any force that is applied on the surface of the body. Like if I have applied P, this is a surface force. Any moment is applied, then that moment is applied because of the effect of some force. That's why the moment is there. So that is also comes in the surface force. Any other force applied on this will be a surface force. What are body forces? Body forces are the natural forces of the body. Like I have this hanging body and this is a mass m. Then there will be one force that comes naturally, which is mg. So this mg is a body force. So if I will be applying some load on this, what will be my load? My load will be P plus mg. My P is a surface force, my mg is a body force. I hope it's very clear. So any forces occurring due to the gravitational effect, due to the magnetic effect of the body, these all are body forces. And surface forces are the any external forces applied on the surface of the body. So by keeping this in mind, I would like you to let's introduce you to the equilibrium equations, and then I will tell you what is the importance of the equilibrium equations, why they are important, what we are going to do in this. So before we do this, let's talk about our typical let's talk about, let me first arrange this for you. Okay, like this. So let's talk about our typical cube that we have. This cube has been extracted from the solid phase inside the body. So you can give the axis to this cube x, y and z. Further, I would like you to convince on this that the stress usually varies. What does I mean by that? That means that stress varies over the surface of the body. When the load is applied P, then the maximum stress occurs here, and then there is some kind of reduction in the stress as it moves here. So stress varies over this body. It does not vary exactly like this I have shown. It does not vary exactly like this I have shown, but in some way or the other, as this is a out of plane loading bending, so there will be high amount of stresses on this fixed point also. So but inside the body the stress varies, and the variation is usually remains linear inside the body. So if I have chosen one small element, the stress will vary on this element also. That means there will be some stress here. If I consider a unit stress here, there will be a unit plus some variation of the stress at this plane. So there will be some variation on these faces. Let's consider a 2D figure that will be much easier to understand. So for the same case, I'll be making a 2D figure from this side. Let's make a 2D figure. Let's say this is a X and Y, and let's say we have a 2D X face. Let's say the distance is dx, and this is also dy. These are unit distances, dx dy. And on this face, as I said, there will be, let's consider that there is unit stress acting on this face, unit stress acting on this face, sigma. So let's say sigma x is acting on this. Then on this face, what will be acting? On this face, there will be some sigma x plus some variation of the sigma s over this element. That means sigma x plus variation of the stress. How will we do this? Del sigma x by del x times dx. So the variation of the stress over this element per unit distance. So variation may be kind of anything here. Let's say, okay, so let's say the variation is like this. Let's say this face is like this. So if this is sigma x, what is this? This is also sigma x. And what is this? This is the variation. This is the variation of the stress. So what will be this value? D sigma x. This will be d sigma x. And what will be this whole value? Let's say this is sigma x dash. So my sigma x dash will be equal to sigma x plus d sigma x. And since this distance is dx, the distance is dx, so you can take, if this is theta, then the tan theta will be, what will be tan theta? Tan theta will be d sigma x by dx. Tan theta will be d sigma x by dx. So what does tan theta represents? Tan theta here represents a slope. It represents a slope of the curve. Represents a slope of the curve. So you can say that your tan theta becomes rather than giving this as d sigma s, let's give this as delta x. So this becomes sigma x plus delta x. This will be much easier. So what will be my delta x? So this is 10 becomes equal to delta x by dx. So I can write this as d sigma x by dx times dx equals to delta x here. And this d here can be replaced with the partial derivative del sigma x by del x, because the stress is varying along the x and along the y also. Since the variation of the stresses along the x and along the y also. So you can convert the direct to partial derivative times dx. Put this here, so sigma x dash becomes sigma x plus del sigma x by del x times dx. So this type of variation, this is you can write down, this is a rate of change of sigma x in x direction when a step of dx is made. So it's a normal stress in the x direction when a step of dx is made. That means there exists some kind of variation over this element, and this variation is in the x direction, and something very similar happens in the y direction also. So what will be the normal stress in the y direction? If I'll consider a normal stress sigma y here, then this will be sigma y plus del sigma y by del y times dy. This will be the variation on this. Similarly, the shear stresses also vary. The shear stresses also vary. Now I will consider them as sigma ij equals to sigma ji. That means they are symmetric. So there will be only one shear stress. I'll write here yx plus del tau yx by del y times dy. So there will be variation in the shear stress also. Correct? And this is tau yx. So now you are going to use the principle of linear momentum here. So sum up all the forces in the x direction equal to 0. When you sum up all the forces in the x direction equal to 0, and also consider a body force. Consider the body force while adding up. Consider x as a body force along the x direction, y as a body force along the y direction, z as a body force along the z direction. So when you add up all of these, then you will be getting your first equilibrium equation in the two dimensions. This equilibrium equation will be del sigma x by del x plus del tau yx by del y plus x equal to 0. This will be your equilibrium equation in the x direction. Del sigma x by del x plus del tau yx by del y plus x, which is the body force. So this becomes your first equilibrium equation. Summation of ffy equal to 0. Then your second equilibrium equation will be xy by del x plus del sigma y by del y plus y equal to 0. This will be your third equilibrium equation in the two dimensions. So this is the equilibrium equations usually in the two dimensions. Remember that the equilibrium equations are also available in the 3D case. So I'm giving you this as a work to do here, that just consider all these forces and sum up to 0. I'm not going to do this for you. You can just write equilibrium equations in the Google and you will find the derivations. Even the images comes as a derivation only. So you can do this by your own. Just sum up all these forces equal to 0 and just consider the dimensions, that dx dy should not be equal to 0. Just consider that, and this will be very easy to prove. Just use the principle of linear momentum here. So now my principle of linear momentum is satisfied, principle of angular momentum, both of them are satisfied. So I'm going to use this in my for the body, to check my body that my body is in equilibrium or not. Now I'm going to show you my equation in the 3D. So these are the 2D equations. I'll show you the equilibrium equations in the third dimension. So now I have written the equilibrium equations for you in the 3D. So these are my final equilibrium equations. I hope you will be going to drive them along, I hope that you will going to drive them along the x, along the y and along the z directions in a 3D, and when you're going to drive them, then you will be getting these three equilibrium equations for you. These equations looks a bit like a complex equations, but they are not so. I would give you an idea of how to learn them. These are very easy to learn. You know the stress tensor. What was the stress tensor? If you know the order of the stresses in the stress tensor, these equations are very easy to learn. We know that first comes sigma xx, then comes tau xy, then comes tau xz, then comes tau, I'll write the same one, xy, then comes sigma y, then comes tau yz. In this way, the other components. So these are the same stress tensor, the derivative of the stress tensor only. That means del sigma x by del x, del tau xy by del y. Just make the derivatives with respect to x, y, z. The components of the derivative with respect to x, y, z, x, y, z, x, y, z. Just add the body forces. These will be your equilibrium equations. So they are very easy to learn. Now, it's very important here to analyze these equations, that these equations are independent of the type of material that we may be using. So these equations are independent of the material. Material dependency will be shown by the stiffness of the material, also known as Young's modulus, and we'll be talking about the Young's modulus afterwards, not now. But you are very much aware that these equilibrium equations will be valid over the surface of the body. They will be valid inside each and every point inside the body, and they does not depend upon any material. Just a differentiation of the stress tensor with respect to x, y and z. The components, and again comes the importance of the components here. So you have to make sure that you remember these. So these equations must be satisfied at every point. So these must be satisfied at every point inside the body. If you have a body like this, at each and every point inside the body, these equilibrium equations must be satisfied. So further, I would like you to analyze these equations as a single variable, like we have done in a for the case of stress tensor. We have seen that we have many equations, and with the help of indical notations, we have summarized this equation in a very simple form, like Ti equals to sigma ij nj. In a similar way, equilibrium equations are also written in this form: sigma ij comma j plus fi equals to 0. So what is sigma ij? Sigma ij is a stress tensor. Comma here means a derivative. If I have written a comma, that means a derivative. So this becomes del sigma ij by del j. So first index is the component. The second index becomes, what is the second index? It's very easy. Just check it here. The second index is your direction, x, y and z, x, y and z, x, y and z. So first index, normal direction. So what does this becomes? Xx by del x plus fi. For the case of x, this becomes x, so fi becomes x, so this becomes a body force in the x direction. For the other cases, the similar will happen. So this is your simple equation for to check out the equilibrium condition inside the body. Correct? And what is the difference in these two equations? What I'm going to tell you will be very important. Very important in the sense that the equilibrium equations will have to be satisfied on each and every point inside the body. Mark my words, the equilibrium equation needs to be satisfied at each and every point inside the body. However, the Cauchy's relation, Ti equals to sigma ij nj, this is the Cauchy's relation, also called as Cauchy's characteristic equation, Cauchy's relation. So this needs to be satisfied on the boundary. But you would like to say that I said that at each and every point inside the body, sigma ij is also there. But I have cut that body. I'm going to cut this body like this. This becomes, and the stress tensor is exposed. So any body you take, you have to cut that body to expose the stress tensor or expose the stress vector, any one of them. So these equations will be applied on the surface, on the outer surface, on the plane. However, the equilibrium equations are satisfied inside the body. So I hope this video will be more informative to you. Remember that intentionally I have not derived the equilibrium equations here so that this video doesn't become so much lengthy. The main aim of this video is to introduce you that why the stress components are rather important than the stress vector, and further what is the importance of the equilibrium equations and why they are used. So I hope this will be informative to you. Thank you, and we'll be meeting in the next one.